My name is Pratik Kumar and I am a third year Metallurgical and Materials Engineering BTech student at NIT Jamshedpur. The topic of my presentation is analyzing different models for predicting critical nugget diameter during resistance spot welding. Resistance spot welding is the dominant process in welding metal sheets in automotive industries. Resistance spot welding is a fusion welding process in which heat is generated by electrical resistance caused by the flow of a localized electric current, and the pressure is applied using copper electrodes to ensure adequate contact between the parts being welded. When the melting point of a metal is reached, it results in the formation of a nugget and an autogenous fusion weld in between the workpieces. Here is a schematic representing resistance spot welding being done between two metal sheets. The quality of resistance spot weld depends on the following features: the fusion zone size or the weld nugget diameter, weld mechanical performance, weld structure, and the failure mode. Failure mode plays an important role in predicting the mechanical strength of the weld. Before talking about the failure modes, I would like to explain the basic terms used during this presentation. BM, base metal. HAZ, heat affected zone. It is the outer area of the spot weld. FZ, fusion zone. It is the inner area of the spot weld. There are three distinct modes in which spot welds can fail. As you can see in the schematic, the first failure mode is pull-out failure mode. In this, the failure occurs via withdrawal of weld nugget from one sheet. The fracture may initiate in the base metal or the heat affected zone. Pull-out failure mode is considered to be a desired failure mode, as in this mode the load bearing capacity increases significantly. The next type of failure is partial interfacial failure, in which the fracture first propagates in the fusion zone and is redirected through the thickness direction. Then the next type of failure is interfacial failure. It occurs by propagation of crack through FZ and has a counterproductive effect on the mechanical properties of spot weld. Generally, the pull-out failure mode is the preferred failure mode due to its higher associated plastic deformation and energy absorption. Mechanical testing. All data used during analyzing and predicting the model were obtained from the tensile shear mechanical test. As you can see in the schematic, care was taken to maintain coplanar alignment during mechanical testing. The quasi-static tensile shear test samples were usually prepared according to ANSI AWS standards. In case of asymmetric specimen, two shims were added to the grip section to ensure tightening and to reduce sheet bonding and nugget rotation. In this study, we analyzed different models predicting critical nugget diameter. Critical nugget diameter is the diameter at which failure mode changes from interfacial mode to pull-out mode. We compared the estimated critical nugget diameter of different grades of steel obtained from different models. The existing industrial standards focuses only on sheet thickness, whereas the other models taken into consideration used a simple fit equation based on limited data of specific grades of steel. A model was proposed to predict failure mode and estimate critical nugget diameter to ensure pull-out failure using MATLAB based on the data obtained from different academic research papers. This model takes into account different metallurgical factors such as weld nugget hardness, hardness of failure zone, along with the sheet thickness, and has been obtained from a larger data set as compared to other models. The reliability of the current model was evaluated using experimental results from literature. Models predicting failure mode. As you can see, all the models given in this slide predict the critical nugget diameter using only sheet thickness. First is the AWS model. It is the industrial model and it holds good for a wide range of material. Next is Chow's model. It is a simplified version of the equation given below. Then the Japanese model, it is conservative as compared to the AWS model, as the data provided is 20% greater than the AWS model. But a drawback of this is that it predicts a higher critical nugget diameter, therefore the risk of expulsion is increased. Next we have the Maria model and the Purnavari model. As you can see that apart from thickness, these model takes into consideration different metallurgical factors like porosity, material dependent coefficient, and the hardness profile of fusion zone. Therefore, prediction of critical nugget diameter is complicated using these models, and they were based on a smaller data set of specific grades of steel. This is a graph between difference of experimental minus predicted critical nugget diameter and the predicted values by different models. The predicted critical nugget diameter is expected to be greater than experimental value to ensure pull-out failure, but the value should not be too high as it will lead to expulsion. As you can see in case of DP600, where the predicted value is too high, it increases the risk of expulsion, and in case of DP780 steel, where the predicted value is too low, it defeats the purpose of the equation. Our equation here takes into consideration safety factor to ensure pull-out failure. As you can see that we have proposed different equations for different materials. There is an equation being proposed in each case, like for the low UTS steel, aluminium alloys DP980 and stainless steel. In each case the error is low and a safety factor is introduced to ensure pull-out failure. In the earlier slides, the equations were for a specific material, whereas in this case, it is a general equation for all the material. In the first case, the sheet thickness along with the ratio of hardness of metal where pull-out failure occurred and the hardness of fusion zone is taken into account, whereas in the second case, the sheet thickness along with a linear relationship of the hardness of the metal and the hardness of the fusion zone is taken into account. The first equation predicts a greater value for the critical nugget diameter than the experimental data in majority cases. The model's reliability was evaluated on a test experiment data obtained from literature. Based on the result, the effect of steel composition on critical nugget diameter was a major factor, especially for sheets with greater thickness, whereas the predicted critical nugget diameter for previous models were not accurate in ensuring pull-out failure. The values predicted by other models were in most cases less than the experimental critical nugget diameter or very high as compared to the critical nugget diameter, therefore highly increasing the risk of expulsion. But in this case, they were usually greater or very close to the experimental data. Thank you.